Good afternoon, students. So welcome back to our online session. In today's session, we are going to continue the same concept of Unit 3 about the periparrot laser diode. So basically, what is the structure of it, periparrot, students? So here we are using one type of laser. That's the laser cavity we do have, and at the one end, this call it as dielectric reflecting layer, from where the reflection is going to take place, and from the other end, from this end, we are going to just see the field strength, how much is the field is going to be considered for that particular laser, and this is a cavity and that is going to be click on 110 crystal planes. This is a crystal plane we do have, and this is a lasing spot, right? What is the thickness of this lasing spot? It is going to take the transverse size, and this is your longitudinal size. So what is your longitudinal size? 250 to 500 micrometer, and this is your transverse size of 0.1 to 0.2 micrometer. This should be the size of the laser, right? What is the laser is all about? Light amplification and your stimulated emission and radiation, right? So we know about the laser. What is the use of the laser? What are the types of laser we do have, and how the laser is going to work? All the kind of things depends upon the laser part we have learned, right? Next thing, how it is going to work for the lateral size. What should be the lateral size for it? It should be around these are the specification we do have, students, for the laser that is designed for periparrot laser diode, and it is optical and carrier confinement layer. So these are the confinement layer you have learned, right? So what is the use of the confinement layer? It's try to protect the laser from the reflecting end to the incident light. So just want to get that kind of part to be conserved from their confinement layers is going to do that, all the kind of part of it. Clear? This is our optical output that is will be coupled into a fiber. So next part we need to see is how it is going to work. What is the personal cavity, resonant cavity for that? So what is the meaning of resonance, students? Normally, what is the meaning of resonance? If one particular part is vibrating, automatically the second part is also get vibrated. Like for example, if you are taken a plate, if you start vibrating the plate, if you start beating the plate, automatically the beside the kind of utensils also start giving the vibration. That is nothing but the because of that second part is also getting into the kind of motion. So that is nothing but resonance we are creating. Same way here in resonant frequency, how much is the lasing threshold value is there for steady state oscillation that needs to occur inside the cavity? How much should be there? So we already have covered, right? P of 12 should be that initial value for that laser, that should be equals to P of 0, and similarly e power minus j beta 12 is equals to always 1. So what is the beta is all about? Beta is nothing but the propagation constant inside the medium. So what is that particular part we are putting over here? We are putting 2 beta L is equals to 2 pi small m. What is this m all about? M is nothing but its integer value. We know that beta, right? So what is the magnitude and phase of written wave? That must be equal to the original wave. Whatever the magnitude and phase response, if at all you want to find out that response value, we have to use this particular relation. So what is the beta? I can write 2 pi n by shift that side value for this 2L. 2L is nothing but the lambda, right? So what I can write for the beta? Beta is 2 pi n by lambda. So this is my beta value. If you want to get the m value from this, I can write as m value, get that from this 2 beta L by 2 pi, right? So this value beta over there. So what is the beta as of now? 2 pi n by lambda, right? So this 2 pi gets cancelled. We get small m. That is m is nothing but integer value for that laser. We can obtain in this format. Clear? So this is the way we can able to obtain the laser integer values. What are the integer values for getting the m? So m is nothing but 2L by lambda m. What is lambda? C by f, right? So this I can write C by f. We had C and f. C is nothing but lambda. So this is the reason we are writing small m is equals to 2L by lambda. If you want to get lambda m, I can write 2 pi by n. So that is nothing but the wavelength inside the medium. How much is the wavelength we are going to give for the laser to get into the propagation medium and to get the resonance frequency to be obtained? That's the reason we are putting a resonance frequency response for that particular laser. Next thing, how much is the resonant frequency? So what is should be the resonance frequency for that? How do we get that? So basically, to get this thing, we should have to know that the cavity resonance, whatever the cavity we are using to get the resonance part to create into it, we can use it and we can create a standard wave pattern when integer numbers m of the half length between the mirrors. When we talk about the mirrors, when the mirror is going to consider the cavity resonance is going to create a standing wave patterns, right? So for that standing wave patterns, we are going to use a mirror. So that mirrors, what is the use of the mirror basically, students? The mirrors are used to find the condition, from that what condition the mirror is going to obtain. So basically, so again is a function of frequency or a wavelength as a condition satisfied for a number of wavelengths. If you, instead of using a one wavelength, if I'm using n number of wavelength, I can also use it for that particular laser. So each of these whatever the values of these frequency that correspond to a mode of oscillation for that lasers. So whatever the frequency we are going to consider, all that frequency is going to use for our laser to get a particular mode of oscillation, right? So by changing the structure, laser can be used in a single mode or it can be used in a multi-mode. So the mode part also we have covered in the previous session, and we have seen how it is going to work and everything, that also we have covered in the previous classes. The basic thing, the relation between the gain and frequency is similar to the Gaussian with lambda naught as a wavelength at a center of spectrum. Whatever the spectrum value, we just want to see how it is get that particular part that is going to obtain by using this relation. What is sigma actually, students? Sigma is nothing but the spectral width of gain. So whatever the gain value, I want to find out that gain value, I can get it with the maximum gain. If I want to find, I can get that with respect to g of 0. What is g of 0? It is proportional to the population inversion. So how we get that? What is the relation for it? So g of lambda is equals to g of 0 e power minus lambda naught square by 2 sigma square. What is the sigma over here? That is the width of the gain. And what is the lambda is all about? We know lambda is a wavelength. Lambda naught is nothing but center of spectrum wavelength. From the center of spectrum, if you want to see the spectral of that particular laser, if you want to obtain it, how much is going to obtain, how much is going to take that value. If you have some sort of senses on that, then we can going to get the resonant frequency for that particular function. How much is the gain? So basic thing is what? If something you are using in any kind of electronics appliances, main concern is our gain, right? So gain factor, we're going to see the functionality, we're going to see its losses, we're going to see its working, constructions and everything. Those are basic kind of thing. In the same scenario, in our laser as well, we are going to see its gain. The basic thing is about the gain. How much is the gain we are going to get that for particular laser? That is our main concern of your that particular discussion. Clear? So students, so this is the value we obtain it for the gain. The next part, what we are going to see is about the resonance frequency. As we said that when we see the resonance, we had a spectral lines, right? This is our wavelength which we are using in nanometer. So it's not showing here. You should write the x-axis wavelength, and y-axis what I'm writing? I'm writing in the lambda. Lambda is nothing but the wavelength, right? This is my central lambda naught. This is my delta lambda, means change in the frequency. This is my 822 nanometer, 824 nanometer, 826 nanometer, 828 nanometer. These are my frequency, these are my wavelengths. If you want to see the wavelength, how much is of resonant frequency I'm going to get? I'm getting the resonant frequency maximum at the central part, that is lambda naught. So we have seen the Gaussian's output profile, we have to see that. So basically to get that profile, we should know the gain, right? As we said, lambda naught is what? Is the wavelength of at center of the spectrum. So as we can see, at this particular spectrum value, this is my center, right? So at that particular center value, my wavelength of that particular wave is maximum. That's the reason we are saying that the resonance frequency of that wave is maximum. Clear? So this is how we can obtain the Gaussian's output profile. So that's the reason we have mentioned here the Gaussian's output. So what are the peaks values it should have at this central between 824 to 826? What could be the value here, students? It can be 825, right? So at that 825, my resonance frequency is at the central point. At this value, this is the maximum part. What actually we are going to get that. Similarly, to get the spacing between the modes of multi-mode laser, if you had not only single mode, if you are using a multi-mode laser, how do we get that? So to get these things, what I can write, for each longitudinal mode, there will be a many transfer modes will be there, right? From the longitudinal mode, if you want to design that, how do we get that? Basically, to get this thing, we should have a multiple modes as well, right? Due to the many reflections that can be going to happen from the sides, as you can see from the laser, right? So from the laser only we have seen there is a longitudinal mode is there, then there is a transfer mode is there due to the reflection from the sides. As we have seen the sides, as you can see from the graph, right? If you see the graph, then only you understand. This is my what kind of part? This is my longitudinal size, right? This is my transfer size, right? This is my reflection layer. This is my confinement layer. So what is the point I'm telling you? Instead of using for a single mode, if at all I'm using a multi-mode, how I'm going to get that? I'm going to get the multiple part of it. How I'm just obtaining that? I'm saying that for each longitudinal mode, there will be a many transfer modes, that is due to the reflection from the sides. From the sides also it can have certain reflections, right? So we have to avoid such kind of reflection, considering the two successive longitudinal modes. For example, the previous value is fm minus 1, the present value would be fm for the integers from m minus 1 and m. If you want to find m minus 1, how do you get m minus 1? By using the relation, the previous relation what we designed it, that we have used for only single mode. Here what we are using? Here we are using for multi-modes. So this is m minus 1 to lambda n c fm minus 1, and this is m also same to lambda n c fm. What is the common in this two? 2 lambda n, sorry, 2l n c. This is common, right? 2l is nothing but the length of that particular wave pattern. If you subtract that, I can write as this mm get cancelled. Here I'll get 1. 2l n by c is common. What is common in this two? 2l n by c. Here I'll write fm minus 1. What is this called? Change in frequency to ft minus f1 is a delta f. So if you want to get delta f, c by 2 pi, sorry, c by 2l caps lock L, uppercase L, and small n. That's how we can able to obtain the spacing between the modes of multi-mode laser. So that's how we can able to find out the values for it by using the multi-mode lasers. Clear? So the laser needs to be very clear for you for the single mode as well as for the multi-mode in order to obtain its analysis. So that's the reason we are taking that particular analysis, and we are using for that particular part, and we are proceeding ahead for our particular lasers. Clear? So now how we get the spacing between the modes of multi-mode lasers, and how we get that? So basically delta f by f you want to find delta lambda by lambda. Clear? What is the delta lambda is all about? It's the lambda square by 2l n, small n. How we get that? This is the spacing between their multi-modes. Whatever the multi-modes if I want to use, if I want to find the separation between that, I can use this formula, and I can able to find out delta lambda is equals to lambda square by 2l small n. Hence, number of modes, their heights, and the spacing depends upon laser constructions. The laser construction is going to obtain that analysis, and we are going to use that laser construction for that particular laser as well. Clear? Next, we need to see its geometricity, how the geometric part of strip part is there. So basically, for DH laser that can provide optical confinement in the vertical direction, but whatever the confinement layers we are using for that our laser, that should be a confinement directional will be there, but lasing take place across whole width. Whatever the laser is going to take, it is going to use for the whole width, but our DH laser that can provide the confinement in a vertical direction only. The broad emission area creates problems like difficult heat sinking. Whatever the heat part is there for that particular sinker, it is going to use it, and it is going to take a sinking. Heat sinking is one of the kind of what we call difficulty in our emission area. So that's what we have to take care of it when we are going for the designing of our lasers. Clear? So the second difficulty is what? Unsuitable light output geometry for efficient coupling to cylindrical figures. Cylindrical fibers, one of the parts what we are going to see for that would be this particular angle only. So for that particular thing, what I am going to use? I am going to use unsuitable light. My light should not be in one direction. That needs to keep on fluctuating. If it is fluctuating, that means we cannot use that one. So what is the main problem with our broad emission area? First is difficult heat sinking. Second part, unsuitable light output geometry for efficient coupling to cylindrical fibers. Also we are going to use it, and we can able to find out. Third point what we have to understand is can be using for the elimination by strip geometry to provide optical confinement in horizontal plane as well. For the horizontal direction also we can able to eliminate the strip geometry. Clear? What is a strip is all about? Strip is act as a guiding mechanism for our lasers. So that's what it is going to give a guiding. How we have waveguides. If you have learned you are going to learn in waveguides about more details in microwave. In microwave you do have a communication subject where you are going to learn in details about how the waveguides is going to be used. Strip acts as a guiding mechanism and provides single transverse mode in horizontal direction as well. That is called as gain guided lasers. That's how the laser is going to use for that guided direction as well. Clear? So because of these all kind of points, what actually we have to conclude in this, that is that whenever we have a laser, when we use for the optical confinement, that should be in optical vertical direction, and when we want to remove the strip geometricity, that should be provide the optical confinement in horizontal direction. That should be eliminated. Clear? What are the problems we're getting in the emission area? When we see the broad emission area, first is difficulty in heat sinking, second is unsuitable light output geometry for efficient coupling to cylindrical fibers. And what are the lasers when we provide a single transverse mode in horizontal direction, that is called as gain guided laser. Clear? So that also the one of the factor what we need to remember when we are going for strip geometricity for that particular laser as well. So that's how this strip geometry we are using for our lasers. What is the strip geometry is all about, students? It can have a two thing. One is the wavelength with relative intensity, and second is wavelength with the same relative intensity. Here first end we are using for higher order horizontal transfer lateral modes, second is we are using for longitudinal modes. As we see, we had longitudinal modes as well as the transverse modes, both the things, right? So when we had a series of wavelength peaks, when we want to see their peaks and how it's going to work on it, the most important thing what you need to remember is it's several waveguides, longitudinal modes, that is having the series of wavelength that is at the peak side. So what we do have, we had at the peak side, when we want to give that particular laser for that peak, it is going to use it. Second part, spacing of mode depends on optical cavity length. So whatever the spaces we are putting, that depends upon how much is the length we are putting in the laser designing. Next, each corresponds to integral number of lengths. Whatever the lengths we are using, at that particular length only it is going to obtain that lasing action. Next part, broadening. Broadening of longitudinal mode peaks due to the higher order horizontal transfer modes. At that horizontal transfer modes also, it's going to perform a certain kind of lasering phenomena. That is also going to be done in our horizontal transverse modes. That should have a peak, right? As you can see, this is a peak, right? What is the wavelength we are using here? 4 nanometer. At that very sharp, this is also the longitudinal, we are getting the modes, and the intensity is very higher, right? Similarly, the strip geometry limits width of optical cavity. It is going to limit the width of the optical cavity and allow only single transverse mode. That gives the good multi-mode laser. So these are the things which we need to consider while we are designing the strip geometry of our laser. Clear? First thing is about series of wavelength, peak for several longitudinal modes. Second part is about spacing of modes depends on optical cavity length. Third, whatever the corresponding to the integer number of length that needs to be there. The broadening of longitudinal modes peaks due to the higher order horizontal transfer modes needs to be obtained so as to get the longitudinal part should be at the higher part. Due to the unrestricted width of action region that needs to be there, and the strip geometry limits width of optical cavity needs to be there, right? And allow only single transverse mode that needs to be obtained, and give good multi-mode laser. That should also be the one of the things which needs to consider while we are designing our strip geometry. For sub peak due to the high order horizontal transfer or lateral mode, these are the sub peak. No, there is a gap between those peaks, as you can see in the graph A, graph number 1, that is I have labeled as A. For the second graph B, this is what, not having that much of gaps in between this, right? This is for longitudinal mode. So students, of the single mode laser, what we just see that is about the single longitudinal and single transfer mode. Both we need to understand, no? So how do we understand that? By reducing the length of cavity until the frequency separation is the larger and the laser transition line width needs to be less. Whatever the rigid control is there for that particular parameter that required to provide and maintain a single mode operation. So the main thing that needs to be achieved by gain guided and index guided laser are this only: the relative intensity and the wavelength of micrometer. If I am using 1.55 micrometer of my wavelength, if I want to use for the longitudinal part of it, the single longitudinal part of it and the single transfer mode, if I want to see for that particular part, I am going to get, this is the graph for intensity. That, see, you are very spike and very thin, right? So that's how the laser is going to use a higher, the kind of, what we can say, it's that kind of intensity of the laser is very fast and very thin, very fine, we can say. Clear? So the gain guided laser portion, how it is going to obtain for the isolated strips. For the isolated strip, if you want to see active gallium arsenate or that bonded by the p type gallium aluminum arsenate region, if you want to see both the things on both the sides, if you see the on the x-axis and the y-axis, if you see both the axes, how it is going to obtain, that can be obtained by using this part, right? N gallium arsenic, N aluminium gallium arsenic, that using the p gallium arsenic active layers by using the metallization and by using the plus part of it, by using p types of aluminium, gallium arsenic. If you use both the ends, from the first end, from the second end, we can able to obtain this as a part of it. One is the confinement now. Another layer for p type and n type. As you can see, n type of aluminium gallium arsenic is there, and here is a p type of aluminium gallium arsenic. Here n type of gallium arsenic is there. Here p type of gallium arsenate is there. This is what high resistivity proton implanted region is there. Here same thing, but the both the end we are using for that, so that the resistive region formed by the proton bombardment give better current confinement. For more bombardment of proton needs to be there, so that the electron can use it, right? It should also give better current confinement as well. For that better current confinement, we are going to use that particular angle, and we are going to use that particular direction based on that, right? So how we get that, all the things that can be obtained, and that can be analysis of that particular region, and we can able to find out that region in one direction as well. Clear? So for that regions, we have to use the gallium arsenic part of it and the gallium aluminium arsenic. Both are active bond by p type region on the both side, and the super thermal. Whatever thermal properties is that due to the absence of silicon dioxide layer, that needs to be there. If you are having all the kind of confinement layers, and if you want to see that how it is going to obtain it, that is also going to be used for the gain guided laser port, gain guided lasers, right? So that is also one of the part of proton isolated strip. Based on that, the proton is going to isolate from one end to the other end as well. Clear? So that's how we can able to obtain it, its relation, its analysis, its functions as well. Clear? So we need to understand the working of it, we need to understand the kind of functionality, we need to see the region of operations and everything for that particular laser. If you want to understand in a better way, you need to clarify all the kind of concepts related to that particular gain guided laser port. Protons isolated strip. If you know the isolated strip for that, then we can able to get the gain guided lasers, right? For PN junctions, that is isolated strips, and by using that regions only we can able to obtain its analysis. Let us see its region as well, right? How the region is going to obtain, what are the parameters the region needs to have, and how the region is going to work on it. Gain guided laser PN junction isolated strip. So here what we do have, we had a selective diffusion through N type phase region, and both types give pure multimode characteristics. And the next part what you need to understand is the highly efficient coupling into the multimode fibers and low coupling efficiency into the single mode. So for the multimode, the efficient coupling is more as we compare with the single mode, right? That because of that reason, we can say the gain guided lasers are more useful for the multimode as we compare with the single mode. Clear? So that's how we can obtain the gain guided part of it. We need to draw it, and we need to explain about the isolated strip. Clear? Next part is index guided. How the index, because index is one who will help the guided part of the laser to obtain in a one direction, right? The one thing about the indium gallium arsenic phosphate, another is what? N-type indium phosphate, another is a P-type indium phosphate, and between that we do have silicon dioxide layer, and we do have P-type indium gallium arsenic phosphate. There are two types of it. One is P-type will behave like, another is N-type, and we are having a substrate and metal. So based on that, how the narrow current confining strip is going to work for it, and what is the current confining strip, students, from where the current is going to obtain it, right? So that should be as narrow as possible in order to get that confinement done. Next thing, the weak index guiding for light that needs to be achieved for the index guided laser, right? So these are the concepts we need to consider for designing the laser part of it. So the index guided laser, that is the next concept. So basically what is the index guided laser, students? The transverse mode control. When we see that particular metal from the region of operation, one is a P type, another is N type, as we have two substrates. In between that we do have N type of gallium arsenic, and another is N is what the P type is supposed to be there. So the reason for the substrates and the kind of medium what we do have, students, so based on that only we are going to understand the index part of it. So always remember, the index part of the laser is taken only the transverse mode of control. We already have seen, right? Waves are of two types. One is a transverse and another is a longitudinal. So we know details of it. I'm not proceeding with in that much. in detail for that transverse mode, we need to understand how the laser phenomena is going to work for us. Because of that reason, we are more concerned about its mode control. So this thing, they said that the buried hetero structure where active region is completely buried in the material, means completely immersed by the material of by whatever the we are using, the BG and lower refractive index, the band gap and the lower refractive index that needs to be obtained for our laser, right? So that's also be the one of the thing that needs to be considered for designing our laser, right? The next part we need to understand is the optical field, well confined in both transverse and lateral directions. So the optical field, whatever we do have, that needs to be confined in that particular direction. The good carrier confinement and the index guiding needs to be there, and the multi-mode and single mode operation needs to be obtained. So because of all these kind of parameters, we can say that our index guided laser is more confined and more part. It's going to take a more amount of index phenomena, right? So it's going to work for the good carrier confinement, and it is also used the index guiding, and the multi-mode and the single mode is going to be taken care of it. So that's the reason we have to consider the confinement analysis needs to be more clear. So because of all these parameters, we can say that our laser needs to be used as an index guiding laser if it has these all features. If it is consist of all these kind of features, then we can say our laser is going to be more confined and it's going to be used for more amount of lasing actions. Next is how the modulation of lasers is going to take place. That is also one of the most important part. We need to understand the modulation of lasers as well. The first thing is about the pulse modulation, and the second thing is about the analog modulation. So those things we are going to understand, and what are the major limitation on modulation rate, how the modulation is going to vary, and what factor the modulation is going to depend. So that is also one of the factor we need to understand while designing the laser, right? Let us proceed with that. So the first limitation for the modulation is about the spontaneous carrier lifetime. That is one of the thing that our laser should be considered while we are designing for its modulation, right? What is the modulation, students? So superimposing the carrier signal with the message signal in order to get the desired information signal at the demodulated end, that is nothing but the output end, if you want to receive that kind of thing. So what is the first limitation we are getting? The spontaneous carrier lifetime. The life of carrier before it combine spontaneously, that needs to have the feature. That means whatever the life of carrier should be there, it should be before it's going to combine with the spontaneously with the message. What is the desired signal? It is a function of semiconductor band structure and the carrier concentration. It should also have a function of both. That is one of the limitation we do have. Also called as radiative lifetime. Next part, at a room temperature, whatever the room temperature we do have, the spontaneous carrier lifetime should be equals to whatever the lifetime is there for our laser, rate of it, that should be equals to obviously 1 nanoseconds in gallium arsenic. Tau of spontaneous is equals to tau of R, that is nothing but rate of it. It should be equals to 1 nanoseconds in gallium arsenic based material for dopant concentration of the order of 10 power 19 per centimeter cube. At this particular rate, the modulation is getting reached. So that is also one of the limitation our laser is going to affect. The next, stimulated carrier lifetime. So that is also have some limitation. One is the limitation is the optical depends upon optical density in the lasing cavity, and it should also have the order of 10 picoseconds. That means whatever the lasing actions we are putting, that is also going to get the stimulate carrier lifetime ST, tau of ST, that have optical density in the lasing action, right? So that should also be less as less possible in order to get the more concentration of it, right? And what is the order for that? It should work 10 picoseconds. Pico means 10 into 10 power minus, pico how much? Micro means 10 power minus 6, pico means 10 power minus 12. Clear? So that should be also one of the limitation for the modulation. The next modulation is photon lifetime, TPH, tau pH actually. So it is what actually, it's the average time that the photon resides in the lasing, whatever the lasing we do have, cavity before being lost either by absorption or by emission through the phases. That is also going to occur. So one other thing is that only the limitation of modulation. I will going to learn in details of it, how it is going to work and everything in the next session. Thank you. Be safe, take care, have a great day, goodbye.